What I want to do here is just do another example with the reference circle and show you how we get the same sort of answers with the reference circle for a pendulum, even though the whole pendulum is a little bit different. Let's remind ourselves of the equations. D equals A sine omega t, V omega A cos omega t, A acceleration minus omega squared A sine omega t, which is the same as minus omega squared d. Now in this example I've got t equals 1.1, it's a pendulum swinging backwards and forwards. I'm going to give it a, I suppose an amplitude, I don't know, 8 centimeters on each side because we need small amplitude. So the thing about the pendulum, remember we're not talking about the arc length being 8 centimeters, we're talking about the distance, the horizontal distance. So that's what I mean as 8 centimeters. Alright, now I think if you watch the other little one on how to use the reference circle, you'll know now that omega becomes pretty important in these problems. Because omega, radians per second, is 2 pi divided by the time it takes to do, sorry I should write that as a big T, time it takes to do 2 radians, which is the period, right? So that's an equation you should remember. Omega equals 2 pi over t. So let's make our question. Let's make it 3 centimeters again. This time I want to know the velocity at that point. So I'm going to use, we know the distance at that point because I gave you the distance from the equilibrium point. So again we can use our reference circle. Although this is a distance, our reference circle tells us the distances. The reason I wanted to show you this pendulum one was because we can still use the same old reference circle. The amplitude is always the amplitude of the oscillating object, which in this case is 8 centimeters. The position away from equilibrium, our equilibrium, we still always project onto a vertical screen. We use the reference circle the same way. We don't turn it around. We always start our clock at equilibrium point, which is that point in the middle. We say that's our amplitude, 8 centimeters. We're asking for it 3 centimeters, what the velocity is. So 3 centimeters, if that's 8, that's going to be about 3 there. So on our reference circle, this needs to be 3, and this needs to be 8. And we want to use the equation V equals omega A cos omega t. We can calculate the angle, we need to calculate that as an angle. Now omega t equals theta, alright, because omega is theta divided by t. So omega t equals theta. Let's work out our omega first. No, let's work out our angle first. Our angle is an inverse sine, right? It's just 3 divided by 8. So if we work out that angle, we'll just do it on our calculator here. We do inverse sine 3 divided by 8, and I've got it in degrees as 22.02, so I'll just call that 22 degrees. So I've said the angle, omega t, equals 22 degrees, equals theta. And we can put that into our, this, don't get confused by that. Remember, if you've already looked at my videos, omega's in radians, t is in seconds, so the actual omega t would be 22 divided by 57.3, because that must be in radians if you're going to try and work backwards and find the t. But as far as on your calculator, if you're doing an angle, if you're in the right, whether that angle is 22 divided by 57.3 radians, if I take the cos of that, it will give me the same answer as the cos of 22 degrees if I've got it in degrees. Make sure you've sorted that out. If that confuses you, come and see me, talk to me about it, we'll get it sorted. Alright, so now we've got the angle, we're ready to go. We still haven't got omega. Omega is 2 pi over t. So that's 3.1 for 6.28 approximately divided by t, which was 1.1. Let's do that in our calculator. And we've got 5.7 is our omega. So Now we're looking good to do our calculation. V equals omega A 5.7 times A 0.08 times the cos of 22 degrees. If I'm in degrees, that's the way I do my equation. I could have gone 5.7 times 0.08 times the cos of 22 over 57.3. And my calculator would be in radians for that one, degrees for that one, and it will give you the same answer. So let's do it. 5.7 times 0.08 times the cos of 22 gives me an answer of 0.4227. So we'll go with 0.42 meters per second. And so you see the key to doing these problems is to work out the angle in these equations, because the angle we get from the reference circle, once we've got the angle, we can work out these things like acceleration and velocity. And that the reference circle, doesn't matter whether your object is a pendulum swinging backwards and forwards or a spring going upwards and downwards, we always use the reference circle in the same way. We didn't work backwards to find the time, did we? Easy enough to do now though. Omega t equals this many radians, which was 22 divided by 57.3. If we divide that whole thing by omega, 5.7, then we'd have the t. Alright, the t to get to 3. Won't actually do it.